isotopes and average atomic mass, so chemical quantities. So, carbon 12, we're looking at regular carbon, right? Because the atomic mass of carbon is 12, right? What we look at is, what does it mean? Well, the mass of one atom of carbon, okay, is 12U. Right? Remember, U represent the units. So another way to look at this is as follows. That 1U represents 1/12 of the mass of one atom of carbon. So if one carbon atom is worth 12, is representing of 12 atomic units, okay, that one atomic unit represents 1/12 of that. Okay. Now, the masses of all other atoms are defined by the relationship to carbon-12. So carbon-12 is what they base it on. So, let's look at oxygen-16. If we look at our periodic table, we'll see that oxygen has an atomic mass of 16. But let's prove it. We find out that that oxygen has a mass that is 133% of the mass of carbon. Okay? Don't worry about how we got this right now. We'll worry about it later on. But this is here a given. So we've given to you that the fact that oxygen is 133% of the mass. So what we do is, whenever we have a percent, okay, we always want to change our percent into a decimal. Right? So how do you change 133% into a decimal? 152. It's one, but how did you get that? Move decimal place. You can move the decimal place, or just divide your number by 100. So anytime you get a percent, you're always dividing that number by 100. Okay? And that will allow us to remove the percent sign and convert it to, as it was stated, 1.33. So we get 1.33, 12.000U. What's that the atomic mass of? Carbon. But we said that 133% of the mass of oxygen is represented by carbon. So we divided these two, multiplied it by 12.000U, and we get 16.0, which represents the atomic mass of oxygen. Okay? So we're going to be doing calculations like this. So what we have is, we have the percentage of oxygen that is related to carbon's atomic mass, and we found out what the atomic mass actually was. Okay. So, now, isotopic abundances. All atoms in a given element do not have the same number of neutrons. They do not have the same mass. They are all composed of varying masses because they include their isotopes. As we said, okay, so if we have here as this example, magnesium having 3 naturally occurring isotopes. What we have here at the bottom, we have a diagram of the magnesium supplement that you can buy at a grocery store, health food store. Okay. That magnesium is not just the magnesium that we know of, okay, having the 24U, the atomic mass of just 24. It consists of all 3 of the isotopes, okay, in varying percentages. Okay, so if we look at the magnesium, okay, in that container, technically 79% of the magnesium in that container, in each one of the pills, consists of your normal magnesium that you'll find in the periodic table. Okay, 10% of it is made up of the isotope, one of the isotopes of magnesium, and 11% is made up of the 26 atomic unit mass for magnesium. So notice here the 2 different isotopes still found within that supplement, magnesium supplement. So anytime you see your formula, so we look at magnesium here, whether it's in the supplement, or here if we're looking at salt water, which is MgOH2, so magnesium hydroxide, that magnesium is made up of these 3 isotopes. Okay, but in the same exact percentage. 79%, 10%, 11% of that. You're not going to have to worry about memorizing these numbers. Okay? We're going to have calculations that we're going to need to do. You will be given these numbers. Okay? Or you'll be asked to find them using the calculations, but we'll go through a couple of examples. Okay? So as we said, regardless of whether it's the magnesium found in one of those two, it is always made up of those three isotopes in this same proportion. 79% of it is of the regular magnesium, 10% of one of the isotopes, 11% of the other. Okay. So the relative amount in which each isotope is present in an element is called the isotopic abundance. It can be expressed as a percent or as a decimal. Okay? Usually if you get the percent, right? Something says, let's say 79%, as we said. Remember, to get rid of the percent, always get rid of the percent by dividing it by 100. Okay, so whenever you get your percent, always divide it by 100, remove your percent sign, and get it into a decimal, because that's how you do your calculations. You turn it into a decimal first before you make any of the calculations. So, when chemists consider the mass of a sample containing billions of atoms, they must take the isotopic abundance into account. Okay, so average atomic mass. The average atomic mass of an element is the average of the masses of all the element's isotopes. So as we said, the magnesium, right, that we found in the supplement or in salt water is within that same proportion. Okay? So that number that we get here, so for this example of carbon here we have 12.01 for the atomic mass, but this is an average atomic mass. Okay? So 6, this is not the chemical notation, this is the way it would appear in your periodic table, with the atomic number up at the top corner, the atomic mass at the bottom. Okay? So what we have here, that the atomic mass that can be found in your periodic table represents the average mass of all the naturally occurring isotopes of the elements. So what we're looking at is we're taking into consideration all these isotopic abundances. The fact that it's not just the 12U of carbon, but it could be the 13, it could be the 14. So which means that we're looking at the atoms of carbon that consists of more neutrons than some of the others. Okay? So, carbon isotopes. Carbon is made up of several isotopes and not just the carbon-12. Okay, that's the one that we know of in terms of our periodic table. Carbon is made up of 3 known naturally occurring isotopes, which we talked about last class. If all these isotopes appear in equal amounts, why is the atomic average, the average atomic mass 12.01? Okay, because if we look at the different carbons, we have carbon that has 12U. We have the carbon-13, and we have the carbon-14. If you were to find the average of all these, right, what would be the average of all 3 of these atomic masses? 13, right? 13. But look at what the actual average atomic mass is, which means carbon-12, right, makes up pretty much the majority of all the carbons that are found in any type of compound. That the isotope is rarely found in the different types of compounds. So if we looked at something like carbon dioxide, 98.9% of the carbons in this formula is made up of the carbon-12. Okay? The carbon-13, 1.1% of it. So 1.1% of the carbons found in all the molecules of carbon dioxide is only going to be 1.1% of the isotope carbon-13, which will have the extra neutron. Okay? And then we have carbon-14. Okay? Carbon-14. Look at how small this percentage is. 1 times 10 to the power of negative 10%. So think of all those zeros. That's how small of a percentage of those isotopes are found in that carbon molecule. Okay? So remember that anytime you see a formula, that formula is made up of the different isotopes. Okay, in carbon, it's regular carbon, the carbon-12, is made up of the majority of all the carbon molecules. Mass spectrometer. How do chemists find the mass of each isotope? They use this mass spectrometer. And what it is, it's a powerful instrument that generates a magnetic field to obtain data about the mass and abundance of atoms and molecules. Okay? You can use the data obtained with the mass spectrometer to calculate the average atomic mass given in a periodic table. We don't have one of these. Okay. So, but using that was how they were able to decipher the fact that carbon makes up 98.9%. Okay, so using that mass spectrometer, they were able to get this value. They were able to get this value. They were able to decipher that that was what was left. Okay. So, calculating average atomic mass. Lithium exists as two isotopes, lithium-7 and lithium-6. Okay. Lithium-7 has a mass of 7.015 U, okay, and makes up 92.58% of lithium. Lithium-6 has a mass of 6.015 U and makes up the remaining 7.42%. But according to our periodic table, what is the mass of lithium?
6.9.
Pardon? 6.9?
Oh, want all of it?
Yeah.
It's 6.941.
6.941, right? So, which one of these is our typical lithium according to our periodic table? Lithium-7, right? So we have a lithium-7 isotope, we have a lithium-6. But notice the atomic masses of both of them. Do they equal the atomic mass that we have in the periodic table? No, because that's the one she gave us. 6.941. Okay, so how do we figure that out? Well, we take this value. Okay, so we take our lithium, lithium-7, okay, and what we do is, well, we take the percentage, so we want to convert 92.58%, so we're going to divide it by 100 to get rid of the percent sign, and we get 0.9258. So we're going to take that value, 0.9258, right? And we're going to find what percentage of that mass is actually of that actual atomic mass. So what we're trying to do, think back to elementary math when you were asked to find percent of a number. Find 5% of 20. So what you're trying to do is, you're trying to find 92.58% of this mass. You're going to try to find the remaining 7.42% of 6.015 units. Okay? So what we have here, so again, 7.42 divided by 100 equals 0.0742. So remember, percentages, we always change to a decimal by dividing by 100. So we get 0.0742 times 6.015. Okay? So all we're doing is we're trying to find a percentage of a number. What's that number? The atomic mass of that isotope. We want to find 92.58% of this atomic mass. We want to find 7.42% of this atomic mass. And then we want to combine them. Okay? So what do we get when we multiply?
6.5.
Pardon? Did you add all of them, or is it just from the top one?
We'll have to add them. We're supposed to add them and multiply.
Ultimately, yeah. So what was this top one?
Our top one was 6.494.
6.494. Okay, and then it continues.
Yeah.
So we need our least number of significant digits, or let's say, well, 3, but we'll worry about that later. Then we multiply the bottom one. And what do we get? 0 point. What'd you get?
Oh, I didn't know.
0.446. So, add those two values. Add these two values. Yes, a calculator would be great. Great tool.
It says 6.936.
Okay, so 6.936. All right? So look at this value here. It's the closest to the actual value in the periodic table. Okay? Of course, maybe if we took all these digits, we would have gotten even closer to that value. But because we already rounded off our numbers, okay, when before we added them, that we didn't get as accurate of a value. Okay, so if we were taking the least number of significant digits is 3, so the value is 6.94U. So notice how, well, the lithium that we know of, really, look at, that's the atomic mass. It's not the 6.94. That 6.94, in fact, was an average atomic mass. It's an average atomic mass of all the different, of all the different isotopes, the 7 and the 6. Okay. So which one do you think we have in most of them? Notice here the percentage, 92.58% is made up of the larger atomic mass. So that's why our real answer, look at where it's closer to. It's closer to the 7.015 than it is to the 6.015 atomic mass number. Okay, because the greater percentages of that higher, okay, of that isotope. Practice problem. Naturally occurring silver exists as two isotopes. From the mass of each isotope and the isotopic abundance listed below, calculate the average atomic mass of silver. Okay, so take a moment, look at this table, okay, and do what we did before to calculate the average atomic mass of silver. Sorry, there is a typo on this thing. So the first silver, we want to convert this to a percentage. 51.8% becomes? Okay, so we have 0.518, and we're going to multiply it by 106.9. Because we want to find out what percent of all the silvers are of this atomic mass. Okay, and then we're going to try to find pretty much 48.2% of that are make up this. So that makes up 55.3742. Okay. This bottom one, okay, we have 0.482% as a decimal. We're going to multiply it by 108.9, and we get 4898. So what are we going to do next? We're going to add these two together. Okay. We're going to add those two together, and we're going to get 107.864. So, according to our question, least number of significant digits are? 3. So we want the 107, but we look at the 0.8, and 107 becomes? 108. What is the atomic mass of silver?
I'm guessing 108.
107.8.
107?
One whole thing.
0.8, right? No, it's just... Okay, so 107.8, but remember, we rounded it off to 108, right? And according to even when you're making your calculations, right, if you're trying to find the atomic mass subtracted by the atomic number to give you the number of neutrons, you always want to round off to your nearest whole atomic mass, right? So 107.8, you'd round off to 108. So notice how
Why do
the
we
two
do
match.
this? Why do we do this?
Because you have to. Now, if you look at these two, okay, they don't compare to the actual atomic mass, right? We're looking at the isotopes, okay, of silver. Okay? Really what we're trying to do is we're trying to understand, well, if I'm going to find the atomic mass, and someone is telling me that the atomic mass of silver is 106.9. I'm going to look at my periodic table and I'm going to say, wait, no, you're lying to me because the atomic mass says it's 107.8. So why is that value not equaling? And we're doing this because we want to figure out why are we getting these. Because in fact, we've been taught that the atomic mass is the atomic mass of all, but we've not been pretty much exposed to the fact that whenever we have a compound, they are really made up of the varying different isotopes. And in fact, that the atomic mass that's given in our periodic table is an average when it's comparing all the different isotopes. Okay? So that's the reason why we're making the calculation. So that's the reason. To understand, well, here I'm telling you 106.9 is the atomic mass of your silver. But you're looking at it and going, no, you're lying.
Yeah, you did.
I did, right? But why? Because the different isotopes play a very big part of figuring out what that is, because that is an average based on the isotopic abundance of each one of the different isotopes. Practice problem. Boron exists as two naturally occurring isotopes. Boron 10, which is 10.01, okay, and boron 11, which is 11.01. Calculate the relative abundance of each isotope of boron. Okay, so let me give you a hint as to what we have. Well, we have first boron, okay, boron 10, boron 11. Boron 10, that's the atomic mass, 10.01. For boron 11, it's 11.01. Okay, it's coincidental, the fact that they're off by just one unit. Okay, not all of them will be like that. We also know that boron, if we look at according to the periodic table, okay, is 10.81, the atomic mass. Okay, so here's the hint. We need that value because we're trying to find the percentages of each value. Okay, so what we have here, now we got to figure out what are the percentage values of each one. So try this one out.
Okay.
Think algebra.
Oh, yeah.
Oh, this is equal this, and then
Right? Because remember, what did we have? We always had that percent, okay, multiplied by the actual atomic mass, right? Whatever our U value is. But we don't have this anymore. So if we don't have that, what are we going to let that represent?
X.
X. But the only problem with letting it equal to X is, well, if we're going to make that one equal to X percentage, and we're going to multiply that by our U value, we can't put them both as X, because if we do, technically, what does that mean?
They're the same.
It means they're really the same.
X.
X
X.
and Y.
X and X. X and Y.
If we add those two together, our two percentages, what should they equal?
100.
100 what? 100%. But whenever we get 100%, remember we want to turn it into a decimal.
Yeah.
So how do we do that?
You have to move this.
You divide it by 100, right? And you get 100 divided by 100 is? So technically, these two represent 100, right? But one is going to be X, the other one is going to be 1 subtracted by x. Because really, what does that 1 represent? The 100%. So whatever that percentage is, it'll represent 100% of it. But we're going to subtract it by whatever that is
Okay.
to figure out what that was. Right? Because let's say we had 45%, 55%. But we said that this was our x. So 1 minus x is, what's the x? We said 55%. Right? But let's say, but remember if it was 100, right? Or if it was, we'll change it to that. Let's get rid of this. Okay, so to keep it, okay, so 1 minus 0.55, right? What is 1 minus 0.55? And what did we say? One of them is 55%. The other one represents 45%.
That was cool.
So that's what it means. And here is what your equation should look like.
No, don't do it yet.
Okay.
Mine has no words.
No, but you're gonna put in numbers in the place of those words. Be careful of the algebra. Let's start a little bit here. So, average atomic mass, what is it? What does this represent here? Okay, so 10.81 equals x, we don't know, right? It's just x. X times the atomic mass of B10, which is 10.01. Plus, we have 1 minus x times the atomic mass of, which is 11 point.
How can you put a 1 minus x in brackets?
Because what we have here is we're multiplying this 1 minus x. We're treating this as a term,
Oh, okay.
right? Because if I don't put them, technically I have 2 terms, right? If I just kept that, in other words, all I'm going to be doing is multiplying my 11.01 by x. But in fact, what I want kind of like a reverse distributive law, where I want this number multiplied within. Okay? So what I have here is 10.81 equals x times 10.01, 10.01 x. 11.01 times 1, 11.01. 11.01 times negative x minus 11.01 x. So what I want to do now is I want to collect my x's on one side of the equal sign and my whole numbers on the other side. Because I want to find the value of, what am I trying to find? Value of x.
Okay.
So, I'm going to bring this over, and I'm going to bring this over, because I'm going to bring x's over this side of the equal sign. Okay, so I'm going to get 11.01x minus, right, because remember this was negative on this side, negative 11.01, it becomes positive on this side. Right? This 10.01x is positive on this side of the equal sign, but when I move it on this side, it becomes negative. Equals. Right? I'm going to keep this term here on this side, and which means I'm going to move this term on that side, and I'm going to get 11.01 minus 10.81. So 11.01x minus 10.01x, 1.01x, which is just x. X is equal to, so when you subtract 11.01 minus 10.81, 0.2, right? Or remember, the least number of significant digits of my question are?
Where is it? I don't know.
4. So 0.2, that's one significant digit. So to add another significant digit?
0.
0, 0, 0. So, but that's not a percent. So I want to change a decimal to a percent.
Times.
I'm going to now multiply it by by 100, right? So 0.2000 as a percent becomes 20. But that's one significant digit. I want 4 significant digits. So what am I going to do?
20.0.
How many is that?
Wait, one more.
One more. Right? Percent. 20%. Which means 20% is of the first boron, right? The boron 10. What percentage is the boron 11?
80.
Okay. Because it will give us a total of 100%. Okay. So that's why we get this 1 minus x. Because remember, what are we changing a percent to? We're changing to 100%. We want to find a total of 100%. But when we find a total of 100%, we change 100% into a decimal, and it becomes 1. So that 1 used to be 100%. 100% minus x, whatever that percentage was.